Okay, good morning, good afternoon, good evening, wherever you are out there. And welcome to the NSF Cybersecurity Summit. And welcome to our tutorial on web security and automated assessment tools. This will be taught jointly by myself, Bart Miller, and Alyssa Hyman. I hope this finds you. I hope this finds you all well. It's certainly a different kind of year, and this is a different kind of format from what we've done in the past. So we're going to try to make this as interactive and as engaging as we can. We appreciate you all being here. We know that we're all spending ridiculous amounts of time in front of screens, and this is going to be 3.5 hours. So we'll try to make it interesting and worth it. Now, we've created this incredible social barrier with the online format. So just normally what we do is we go around the table and ask everybody, what's your background? How many of you are programmers, analysts? And that's a little awkward here. So what I'd like to do is something a little funny. It's like everybody just unmute yourself for a second, just say hi, so we know we're actually talking to real people out there.
Hello.
Hi.
Hi.
Hi. Hello.
Great. Thank you all. It's actually good to hear your voices and know you're out there. And hopefully things are going okay for everybody. All right. So a brief bit of logistics, and I'll remind you again in a few slides. But for the to ask questions, what we'd like you to do is you're sitting there on Whova with a Zoom window inside of it. So in the Zoom window, there is a place to click to raise your hand. So when you want to ask a question, if it should be at the bottom of your screen, I understand. Just click on raise your hand, and then either Alyssa and I will call on you, and then you'll unmute your mic and ask your question. We'll do our best to answer it, of course, and do that. So that way we can keep some semblance of order there. So please feel free. We do want questions. Okay, so let's get started. Next slide, please. Just to start out with, why why we're teaching this, and because this is kind of what we do. We go out there, and those of you who have seen the announcements for engagements from Trusted CI know that one of the things that goes on is we go out and do assessments of your software. We do in-depth assessments of the software. We've been doing this for many years. We've done it through Trusted CI. We've done it through other venues. We've done it for the government. We've done it for companies, where we go in and look at people's code and try to find things wrong with the code and try to find holes in that code and then help those fix it. So we are kind of boots on the ground, get our hands dirty software analysts as part of what we do. One of the other things we do, and as a result of doing that, and a result of seeing people doing the same kind of mistakes over and again, we started developing training material. And so so what we do now quite often is we teach tutorials like we're teaching here to you, users, developers, admins. We also teach classes. We developed a whole semester curriculum around this general area we call Introduction to Software Security, which we've introduced here at the University of Wisconsin, and we have online teaching resources as well. So, and then we're also university researchers and faculty. We do research into making these techniques more efficient. And we're happy to talk with you about any of those issues. Next slide, please. So just as I said, we've done a bunch of assessments. And so, for example, one of the first ones we did many years ago was HD Condor. We've done Google Chrome for Google, things like MyProxy, Identity Management. We do Wireshark for the Homeland Security and Department of Justice. Interesting story. Done some other stuff in various middleware components. And we've even done stuff, been working in cybersecurity in the maritime shipping domain, trying to make container shipping, which is 90% of the world's commerce, international commerce, go more safely. So we've been doing a lot of this. Okay, next slide. So here is the general format of what we're going to do. I'm talking right now, that's the first few minutes. Then we're going to switch to videos for each topic. Instead of trying to do it ad hoc, we're going to switch to videos. At the end of the video, we'll switch back to a live Q&A session. So we're going to alternate between videos and live Q&A. Then at 1 hour and 35 minutes into the presentation, we'll have a half-hour break where we would sit and chat with you for coffee, but we'll have to get our own separate virtual coffees to get. And then we'll switch. We'll do one more video about tools, and then we'll switch to hands-on, which will be a live. This is Alyssa will be running a live hands-on exercise with you. So let me see, and then one more thing, and is that if you have not downloaded and installed, if you don't have VirtualBox running, you really need to install VirtualBox and get the virtual machine downloaded here. So let me do two things. One, first, to see if there's any immediate questions that anybody has before we start out. Okay, Alyssa, is there anything you want to say about the preparation for
Just, that's the same link to the virtual machine image I sent you all email some days ago, but in case you haven't downloaded, please start downloading now. Don't wait until we start with the hands-on exercises, because the downloading takes some time. So if you have not done that, please do it now, because kind of the hands-on part, sorry about that, the hands-on part is the funnier part of the tutorial. Okay, so let's start with our first technical part in the tutorial here. So sorry, for this video, the volume is a bit low. The rest of the videos have the standard volume. So you may, but we have captions for this video.
In this module, I'll be introducing you to some basic concepts needed to describe an attack. As part of this introduction, I'll give you some insights on how an attacker thinks about the code they are attacking. So, the objectives of this module are first to learn some of the basic vocabulary of an attack. With this vocabulary, we will learn the basic concepts underlying an attack. We will then make these ideas more concrete with a real-world example, the classic stack smashing attack. Throughout this lecture, we'll be talking about how the bad guys might think. After all, to put up a good defense, you have to learn to think like the bad guys. Attackers think about code differently than the typical programmer, and differently than most of us are taught in our programming courses. The attacker will be immediately drawn to the limits of your program, exploring where you enforce or don't enforce those limits. In this picture, the gate is only useful if there are no other easier ways to enter. Of course, from the tire tracks in the picture, we can see that people figured out the limits pretty quickly. Let's look at the idea of a security exploit through the eyes of an experienced attacker. An attacker thinks about how their actions can affect the internal state of your program. Their goal is to change the internal state of your program in a way that you didn't anticipate or desire. For example, if the attacker typed their name in the field of a web form and submitted that form to your server, their name would end up in a buffer in your program. So, in effect, they control the state of the bits in that buffer. We say they own those bits. And that's okay and intended. However, if their input in the web form was too big
for your buffer and caused it to overflow, then they would have changed values outside of the buffer. They now own bits in your program that you did not intend, and that could be very bad. So let's follow the path of an attack. We start outside the program, listing all the places where an attacker can affect your program. This is the attack surface. The web buffer I just mentioned is one point on the attack surface. Your program processes whatever input the attacker provides, following the flow of the program until the intended bad thing happens, such as extracting a file or obtaining root permission or administrator permission. These bad things form the points on the impact surface. Let's think about these terms by describing a non-computer example of an exploit. Suppose you want to rob a bank. Let's look at some examples describing the attack surface, the path of an attack, weaknesses, and impact surface. The first example has the attacker approaching the bank in the most obvious way, through the front door. The steps of an attack are to request some cash as a normal customer, then have an accomplice distract the teller so that the attacker could quickly reach over the counter and remove some cash from the drawer. The weaknesses here are a narrow counter with no barrier and a teller who turns away from their drawer while it is open. The impact point is removal of cash from the drawer. Our second example has the attacker entering the bank through the back door. If they're able to enter, then they see if the bank vault is open. It's frequent during normal business hours. See if any cash is around, and then grab the cash and run. The weaknesses here would be a back door left unlocked, a vault left open, and cash left unlocked. The impact point is removal of the cash from the vault. Of course, we could also consider a way to come in through the window, but let's look at another more interesting attack. What happens if one of the employees, the teller in this case, is dishonest? Here, the path of an attack is simple. The teller removes cash from the drawer and hides it. The weakness here would be inadequate background checks on the employees and insufficient inspections and audits to catch the problem. Note that this is an example of a serious problem that could occur in any organization, the insider threat. Now let's look at our basic terminology in more detail, starting with the attack surface. Suppose you have a running program like a server. There are a variety of ways that an attacker can affect the execution of that program. For example, it's likely that the outside world will communicate with the program through common network protocols. The structure of the data in the messages sent to the program can affect its execution. If the program is given an input file, the data in that input file can affect its execution. If a program acts as a web server, the input fields from the web form sent to the server will affect its behavior. If a program reads from a database, and the entries in that database come from another program or user, that data can affect the program. A more complex example happens when you can control the starting of a privileged program called setuid in the Unix world. The setting of your environment variables or the parameters that you pass to that program can affect its behavior. As we've discussed, the attack surface should describe all the ways that a user can affect a program's behavior. Sometimes an attack surface is obvious when dealing with direct attacks. A direct attack means that the user is interacting directly with the program. For example, the user sends a packet or web form that is processed by the program. Other times, it is more difficult to see what is actually being attacked. We call these cases indirect attacks. Consider this example of a user sending requests to a server. As is the case with many systems, the server might log unusual events such as errors and suspected attacks. Sometime later, perhaps once or twice a day, a separate program running on an isolated server will scan the log file for events that should be reported to the operators. The first step is, of course, for the user to send a request to the server. Let's assume that this request comes from a malicious user who is trying to attack the server. Your server is well designed and detects that the request is bad. It rejects the request, logging the event, and then responding with an error to the user. Sometime later, the log reader service wakes up and processes the log file. The problem is that the attacker carefully crafted some of the data in the request message to cause the log reader to misbehave, in effect attacking the log reader service. This is a real-world scenario. In our software assessment activities, we have been able to attack systems in this very way. Since users cannot directly access the log reader, the programmers assumed that it was less security critical than the server. Unfortunately, through the log file, the attack surface could reach all the way to the log reader. Once we know how the user input reaches the program, then we need to understand what the program will subsequently do. We have to follow the execution of the program through the code, ultimately seeing if it can reach dangerous operations. Following the execution of the code means following both the control flow and data flow of the program. The control flow follows all the loops, branches, and calls in the code. Data flow can be more intricate. Let's look at an example of the data flow in this small code sample. Suppose that variable I came from the input, and we wanted to see which other variables are affected by I. I is first used as a subscript to the array buffer, producing a value for A. A is then used in a calculation to produce B. And finally, B is used as an index into string table, producing a result that is printed. Usually, you have to look at a combination of both the control and data flow to understand how results are computed. In this simple example, the value of input buffer sub 1 affects the value assigned to val, but in a much messier, complicated way. As we follow the flow from a point on the attack surface through the code, we can end up in a place in the program's code where something bad might happen. Here we see a call to a function that might allow dangerous user code to run. We're concerned about such things as places in the code where the user can cause programs to execute any code they want, give the user access to a file or other resources to which they are not entitled, allow them to act as if they were someone else, forward an attack to another computer, or disclose inappropriate information. Together, all the places in a program that might allow a user to do inappropriate activities is called the impact surface. Now, let's take the things we've learned and use them to understand a truly classic security vulnerability, stack smashing, based on a buffer overrun vulnerability. This vulnerability dates back to the Robert Morris Jr. Internet worm from 1988 that brought the then nascent internet to its knees. Let's start with a simple function written in C. It declares 3 local variables it could allocate on the stack: buffer, I, and j. As is common, the return address for this function is also stored in the stack. We can see that buffer is an array of characters, 8-bit integers, with a length of 100. Right away, we can see that this code is problematic, as there is a constant 100 buried in the code. Definitely a worrisome practice. The main action of the function is to input a character string from standard input using the dangerously simple getS library function. getS is dangerous because it has no way to specify the maximum length of input, making it easy to overflow buffer. In fact, this is exactly the same function that allowed the Morris worm to mount a successful attack. Now let's suppose an attacker feeds a long input string to this function. The first 100 bytes will fill up buffer, and the next bytes overflow in adjacent memory, in this case overwriting the return address. If the attacker carefully chooses the value to overwrite the return address, when the function returns, it will go to the location of the attacker's choice, effectively changing the behavior of the return into an attacker-controlled jump. From an owning the bits perspective, the attacker owns the contents of the input buffer, and that's expected and okay. However, they are able to own the adjacent bits that store the function return address, and that's definitely not okay. This example was a simple one, where the input directly modified the target bits, and there was no complex controller data flows to contend with. Also, the attacker could cleanly own all the bits in the return address, and no timing issues or race conditions were involved. System designers have been busy trying to make these attacks more difficult. Some of the ways in which they've done that include using a different memory location for stack, heap, and much of the code each time the program runs. Such address space layout randomization makes it harder for the attacker to pick a reasonable address to jump to, even if you can overflow a buffer. The designers have also added internal checks to ensure that the heap and stack haven't been tampered with. These mechanisms are called heap guards and stack canaries. There are also new features that don't allow a program to write into its own memory and then execute newly written code. While these features are pretty effective and appear in most modern operating systems and processors, attackers occasionally find new ways around them. In this module, we revisited the notion of an exploit through the eyes of an attacker, learning about the concept of owning the bits. We introduced some important terminology and then used it to better understand the classic stack smashing attack.
Okay. Good. Hopefully people found that interesting, a little bit different view of how to think about your program. There a question came in on the chat about what do you need to do to participate later. There was Alyssa, can you briefly go back to this to the presentation, to slide 7, so we slide 6, I mean, so we can get the link up there on the screen. Meanwhile, let me see if anybody has any questions or comments about what we saw in the first few minutes there.
Okay, here is the link.
Perfect. So if you were going to do the hands-on part, remember.
In this module, I'll be talking about
Uh-oh, I'm attacking myself. Remember that you'll need to have VirtualBox installed on your computer, and it runs on just about every kind of OS there is. And then you'll need this virtual machine, which contains the exercises in it. Okay. Okay, and somebody posted that link to the chat window. Thank you very much. Okay, any other questions or comments before we move on to the next section?
But we have a hand raised.
Okay, oh, there. Okay, Pete, please.
Yeah, I just wanted to give a heads up. I installed VirtualBox yesterday. I installed the latest version, 6.1.14, and it kept dying with that image. And with Elisa's help, I went back, installed to 6.1.12, and it worked. So I just want to give anyone a heads up who's installing VirtualBox from their site to go to 6.1.12 instead of 14.
That for the Mac, because on
okay, yeah,
on Windows the last version 14 was working fine.
Okay, yeah, Mac. I'm on a Mac, obviously. Yeah, thanks. Just wanted to clarify.
Thank you for that. Okay, any other questions or comments? Okay, somebody said they had no problem using the latest. Okay. Yeah. We'll help anybody that's got problems. If you didn't have problems, go for it. Okay, so we're going to start with talking about the first section in web security.
In this module, I'll be talking about threats and attacks that affect web applications. This module is divided into 5 parts. This is the first part of the web module while presenting some background material on the web. Parts 2 and 3 will discuss cross-site attacks. Part 4 will discuss the basics of web session management, and Part 5 will discuss attacks related to redirection. For this first part, our objective is to learn some basic concepts that we'll use in our discussion of web attacks and vulnerabilities. Note that web security is a huge topic, and web technology is constantly evolving. These modules will give you the background that you need to understand the basics. If you're a web practitioner, you need to stay alert for new developments and study the specifics of the frameworks in which you work. The material in the web modules will help you understand these developments and frameworks. Let's start off with the protocol that underlies web requests and responses, HTTP. Here's an example of a simple request from a web browser or any other client that might generate a web request and a web server. The request was generated from the URL we see here. This translates to a simple GET method that will return some data from the web application, in other words, the web server. The request can include a variety of header types. Here we include a minimal set that specifies the protocol version, HTTP 1.1, and what was the user agent, the Mozilla 4.0 browser, and the language encoding, US English. The user agent is particularly useful to help ensure that the user agent is compatible with the web server. Incompatibilities can come from different protocol versions or from using vendor-specific features or characteristics. Now let's look at the response to that simple HTTP request. It's going to contain two parts, the response header and the body, which has the contents of the actual web page being returned to us. In this case, as is common, the web page is encoded in HTML. This header tells us things like the protocol version and the all-important response status code. In this case, it is 200, which means that a GET, PUT, POST, HEAD, or TRACE HTTP method completed successfully. There are other success responses in the 200 range that you might see, but 200 is usually the most common success status code. We also see information about the server and its version. Then there is a timestamp for the response and information about the web page itself, such as when it was last modified, its length, and content encoding. Last but not least, we have the actual HTML for the web page. As I mentioned previously, there are a lot more header types, and we'll mention a few more of them throughout the web modules. The original HTTP protocol was concerned with how to format requests and responses. No real thought was given to security. As a result, there's no form of encryption or authentication when you're using HTTP. In 1994, Netscape Communication, the company that produced an important early web browser, developed HTTPS, the first version of HTTP that provided for encrypted communication between the web client, the browser, and the web server, the application. In 2000, HTTPS became an internet standard with the release of RFC 2818. The encryption was based on the original Secure Sockets Layer, SSL protocol, and is based on the use of a digital certificate, which also provides authentication of the server to the client. We'll talk more about HTTP versus HTTPS in the module on session management. However, just a preview of that discussion. As a general rule, avoid HTTP at all costs. Without encrypted connections, it is difficult to provide any reasonable level of security when accessing the web. The various types of requests that can be made to a web server are called methods, with three of the most commonly used being GET, POST, and PUT. We'll base the rest of our web security discussion on these three. From there, you can use that background to understand most issues with other methods. GET is the simplest of the methods. It requests content from the web server where the intent is that the request has no side effects. In other words, making a GET request doesn't change the state of the data being maintained by the server. As a result, you can hit the reload button on your web browser without causing any unexpected effects, like buying 2 airline tickets when you intended to buy only 1. The request can be completely contained in the URL. POST makes a request to the server that will cause an update to the data stored in the server. If you repeat the request, it likely will cause an additional update, like maybe buying a second unintended ticket. The contents of the request are contained within the HTTP request. PUT is a request that also makes a change to the state of the server. But in this case, the update to the data is idempotent. This means performing a given PUT operation once should have the same resulting change as if you repeated the PUT operation many times. Note that the conventions about whether a given method has side effects or is idempotent are just conventions. They are important conventions and should be followed, but there's nothing to keep the web programmer from implementing, for example, a GET request that has side effects. Even if you use a web framework, you can still make this kind of mistake. Such a practice is sloppy and error-prone, but does happen in the real world. It's worth carefully auditing your web applications to check whether you're doing this correctly. Cookie is a cute term for small pieces of data that a web server returns to the client along with a response page. When you make a subsequent request to the same server, the cookies that you received previously are automatically sent to the server along with the request. In our example, a client makes a request to their bank, and along with the request are sent a couple of cookies. Contained in the bank's response is a new cookie that contains, for example, the ID of the current banking session. When the client makes its next request to the bank, that request will contain all the cookies for that site, including the newly sent one. Cookies are intended to maintain state in the client about what it is doing on the server. So they might describe your session name, more about that later, whether you clicked on some permission form, or what page you last visited on the website. A critical part of web security is based on a property called the same origin policy. This policy tries to prevent a web page from one website from interfering with the web pages from another site. Suppose you had a couple of web pages open in your browser, one from the University of Wisconsin Computer Sciences and one from the City of Madison. As we can see, the URLs have different domain names for their websites. The browser stores a bunch of information for each of these windows in something called the DOM, the Document Object Model. This information is available to scripts, in other words, JavaScript, running in a window. There's a long list of things stored in the DOM, but a couple of the most interesting and well-known items are the list of cookies for that website in that browser window, and a list of images displayed on that web page. The same origin policy controls which of this DOM information can be accessed by a script running in a particular window. That is, a script in a window can access information associated only with its own window or other windows having the same domain name. So, in the browser example we see here, scripts running in the left and center windows can share DOM information and, in fact, share the same collection of cookies. The window on the right cannot access any of the information from the other two windows. Enforcing the same origin policy is important because a web page can contain references to pages from other domains. Such references are common. For example, a web page may include an image tag that uses a URL to reference an image from another website. We also see such references in JavaScript, frames, and style sheets. As we'll see in the next module, the goal is to prevent a web page from one site causing an attack on another site.
Okay. Hopefully there were some reasonable things you learned in that session and on that that video. Just some basic backgrounds. Probably that's familiar for a lot of you, but might be review or cleaned up a few gaps for others. See if there are any questions or comments for this before we jump into various kinds of attacks. Okay, well then, what we'll do now is that we will go on to the next unit. And so we're going to go through cross-site scripting, cross-site request forgery, and then cross-site request forgery mitigations, and then session management. Those are all, and really it all ties together when we get to the session management section. Ties it all the pieces nicely together. And just as a quick bit of background, this is just in the last several months, we redid completely our web security curriculum. And so what we had was okay before, but we really dug in, picked up kind of the latest best practices, and try to come up with a real strong, better pedagogy for that. So you're hopefully benefiting from that.
Yeah, and all the pieces that Bart was mentioning, you will have the chance to really, experience them in the hands-on part later today.
Right. This is all stuff we're gonna go from theory to practice in the hands-on. Okay, let's take it away with cross-site scripting.
Coming. 1 second.
Stand by, we're getting there. It's a little bit of a juggle.
It's not sharing, right?
Not yet, no.
Okay, so I have an issue here. Okay.
In this module, I'll be talking about threats and attacks that affect web applications. For this part of the web attacks discussion, our objective is to learn about how cross-site scripting works and a server-side technique to prevent such attacks. We'll start by introducing something called cross-site scripting. You can think of it as a form of an injection attack where the language being interpreted is HTML and your browser is running the interpreter. The attacker's goal is to get your browser to execute HTML that contains something that might be harmful to you, such as HTML tags or JavaScript code. Of course, web pages contain tags in JavaScript normally, so the goal is to prevent your browser from executing dangerous ones. The evil HTML might get introduced into a web page in a couple of ways. One way is caused by convincing you somehow to send a URL to a server that causes evil HTML to be reflected back from that server. The second way can happen when a web server includes content from a database when it constructs a web page. For example, when a website includes user feedback or reviews, these are usually stored in a database. When you request the web page about a certain restaurant or product, the web server will query the database and get the reviews and include them in the web page. If an attacker had put malicious content in the review, and if the web server didn't neutralize this content, the attacker might be able to cause bad things to happen to the web user. Neutralizing can be done by the web server, not client, by preventing the unexpected tags or JavaScript to be included in the returned web page. This neutralization can be done either when the information is put into the database or when it is read from the database. Let's look at a mechanism that would allow cross-site scripting. We'll start with an innocent example and build from there. Consider a URL for a simple web request to example.com. This request contains a parameter q that has the value of the string widget. When this simple web server is processing the request, it will look for a parameter called q and get its value. If the value is present, it'll put some text into the web page that says you looked for, plus the text that was in the URL, which was widget in this case. The HTML that gets returned to you contains this text. Now, this idea of information from a web request getting reflected back into HTML on your web page is a pretty common scenario. This is normal behavior that we frequently see from websites. For example, maybe I typed in BART as my username into a web form. So this string BART was included in the web request. Once I successfully logged in, I would likely to see some kind of message like, "Welcome back, user BART." So nothing bad or surprising. Now let's change the URL to include a parameter that's a bit more interesting. This one contains script tags, which indicate, of course, that the stuff between the tags is JavaScript. Now, when the web server processes the query, it'll put the text script alert boo close script into the web page. And when we view the web page, a pop-up alert window will appear with the message boo. Nothing particularly bad happened this time. But the web request did cause the server to send back JavaScript that was then executed by my browser. Now let's see where cross-site scripting get more problematic. In this example, the JavaScript is now accessing the list of cookies stored in the DOM for this web page. Of course, this does not yet look that bad because they are just being displayed in the browser window. Let's see how to leverage this mechanism to do something more worrisome. Here in the reflected JavaScript, we're doing something a bit trickier. We first create a new image object and then assign a URL to the object that will be used when the object is referenced. The URL is concatenated from two parts. The first part is a reference to a website chosen by the attacker. The second part is the list of cookies for this current window. So the result of this concatenation is a URL that is sent to evil.com, but contains the cookies from my current window from a completely different website. And this list of cookies might contain risky data like session IDs. And the same origin policy doesn't help here. Not good. And we can see that even major organizations like Twitter and Facebook have had problems in the past with cross-site attacks. And we're likely to see more such attacks in the future. Back to our example, we can see how the server can help prevent cross-site attacks. Here we look at the parameter value to see if the string from beginning, that's the caret character, to the end, that's the $sign, has all its characters matching characters that appear in normal English words. In other words, does the string consist of only letters or digits? This is a form of whitelist. So if you have other characters like the greater than or less than sign that indicates an HTML tag, the text will not be inserted into the web page. Note that this solution is targeted at text for English language. If you wanted to handle alphabets for more languages, you would have to design a more complex test condition. We are dependent upon the server to do this right, so we hope that every website that we visit has been careful about preventing such attacks. In this part, we introduced cross-site scripting attacks and showed how you could leak information with such an attack. We then described the simple mechanism on the server side to prevent such attacks.
Okay, welcome back again. So what we did here was look at the first possibilities of how people can manipulate a web session using these cross-site attacks, and we talked about basically how that looked, how you could deal with that on the server side. And then we talked about also the exfilling cookies, which is problematic. So let me see if there are any questions on what we've talked about so far, or any comments. You guys are a very quiet audience, and either we're super clear or we've put you all to sleep. Okay, well, let's move on to the interesting and serious issue related to cross-site request forgery. So this is a different and very powerful way attackers have and still do manipulate web sessions to try to cause bad things to happen. So what we're going to do now is talk about how that works and what the bad thing is going to happen, and then we'll start talking about after that we'll get talking about how to fix it. So we'll go from the problem to good session management in the following video unit. So let's take it away with cross-site request forgery.
In this module, I'll be talking about threats and attacks that affect web applications. Our objective is to learn about how cross-site request forgeries work. This type of attack has been particularly widespread and harmful. In the next part, we'll address web session management and how to prevent such attacks. Suppose an attacker caused you to execute some HTML that you didn't intend. What kind of bad side effects could happen from such an occurrence? Basically, the attacker might cause your browser to generate any web request that they want. And if they have done this cleverly, might convince your web browser to cause unintended bank transfers, purchases, or postings to social media. Note that this last item, unintended postings, can be more serious than what you think. Such postings can damage reputations and cause financial or social disruptions. So, simply loading the wrong web page could set you up for serious problems. The basic idea is that if you load the wrong web page that contains HTML tags or JavaScript, this might cause your web browser to trigger a problematic web operation. For example, if the web page that you visited has an image tag, that tag will contain a file name or URL pointing to the image text. That URL can be designed to try to trigger an operation on your bank account. Such an attack assumes that you're already logged into your account at the bank. Otherwise, it will quietly fail. Of course, since cookies are automatically sent with each web request, your session ID will be sent along for free. When your browser generates a web request, the web application, the server, cannot tell if you generated it intentionally or as a side effect of an attack. And, of course, using an encrypted channel does not do anything to prevent such attacks. With HTTPS, you've just been securely hacked. Let's walk through an example of how an attack might cause you to make an unintended bank transfer. We'll start by assuming that you have previously logged onto your bank's website. In the process of logging on, your browser sent along the existing cookies to bank.com. Assuming that you logged in correctly, the bank will respond. The response will likely include a new cookie that contains your ID for your current banking session. Sometime later, probably in a different window, you visited an inappropriate site. Maybe the site was caused by clicking in the wrong link, or mistyping a URL, or just bad judgment on your part, or because you were lured with an ad for a new bike for under $50. That inappropriate website returned a web page that contains an image tag, and that tag contains a URL which triggers a request to your bank to transfer $1,000 to the nefarious Evil 37. Of course, since this request originated from your browser, the cookies that you have for bank.com will be sent along automatically, including the recently acquired session ID. And for those of you who are experienced web programmers, at this point, you might be complaining about the example web request. The request in the URL is a GET request. That, as we discussed in the background part, should not cause any side effects. We use this type of request for conciseness in the diagrams. But in this banking example, an account transfer clearly has side effects. And if you are programming in a web framework, you can easily specify which web application methods get triggered from GET, POST, or whatever. But it's also easy to specify this incorrectly and worth auditing your web applications to see if you've done this correctly. But never fear, it is easy to create a web page that contains an attack based on a POST request. In this example, we have some JavaScript that first creates a new request object. Don't worry that it says XML request, that's just the name. We initialize this request object with the details of the post request that we want to execute, and then actually trigger the request. Note that this request gets triggered without the user clicking on anything. And if one way to generate the attack isn't enough, here's a second way. In this case, we're using web forms with some interesting options. Web forms are normally used to fill in fields, select pull-down menus, and click on buttons. In this attack, we're constructing a web form for a post request. However, you'll note that each field of the form is hidden, so it does not appear in the window. Second, there's a bit of JavaScript added to actually submit the form without needing the user to push any buttons. Now back to our original attack example, where visiting the wrong web page caused your browser to generate an inappropriate web request. The consequence of this request succeeding is that money is taken out of your account and sent to an account controlled by the attacker. Not good. To wrap up, we introduced cross-site request forgery attacks and showed how they can do something harmful. This presentation lays the groundwork for the next part, where we discuss how to manage a session to prevent such attacks.
Okay, great. So we got to see a little bit about how an attacker would try to manipulate your web accesses and cause well, a variety of bad things, causing you to perhaps generate actions which you didn't intend to do, which could have bad consequences. So let's see if there's any questions on that now. A question says, do we know if any security endpoint vendors specifically attempt to adverse cross-site request forgeries? These are difficult to do without knowing what's going on in the browser. Because typically when you're generating, the bad action you generate is a legitimate action. It's just not an action you might have chose to do. So I don't know of any of the endpoint vendors that are able to avert it. Most of the work I know to prevent cross-site request forgery happens in the browser trying to do things right. And then we'll see in this upcoming section that if you as the web application designer, the person who built the web server, design your server and session correctly, you build sessions correctly, then you can make these kind of attacks very, very difficult. I never say impossible, because in the security world, somebody always comes up with something eventually, but let's just say very, very difficult for right now, which is as good as it gets. And that's a good question. Other questions? See, I'm looking around the room at all of you, so just to make sure I'm just catching all of you. So I'm looking at you now, so it's your turn to ask a question. Okay, good enough. Okay, let's go on to, let's tie these pieces together with the concept of session management.
In this module, I'll be talking about threats and attacks that affect web applications. Our objective is to learn three important components of web session management: secure connections, session IDs, and nonces. If you correctly combine these, you should be resistant to cross-site request forgery attacks. In the previous part of this module, we discussed how a cross-site request forgery attack works. In this part, we'll talk about three important parts of managing a web session to be resistant to these attacks. We're going to discuss three things that you need to get right to be resistant to cross-site request forgeries and related types of attacks. First, you need to have a secure connection. This means never using an unencrypted HTTP connection. Second, you need to correctly generate and use session IDs. Third, you need a way to show that a web request originated from the user and not from a cross-site attack. We'll add hard-to-guess tokens called nonces to our request to accomplish this. Now let's discuss each of these three things in more detail. The first thing is pretty simple. Make sure that all your connections to the web server are authenticated and encrypted. This means avoiding HTTP connections and always using HTTPS. As Hamlet might have asked, to encrypt or not encrypt? That is the question. For us, the answer is easy. Always encrypt. We're seeing a steady stream of advice from government, industry, and academia against using HTTP. For example, the website cio.gov, which provides advice and guidance to CIOs and the US government agencies, is quite clear. A White House Office of Management and Budget memo says, always use HTTPS. And in the mobile world, Apple will only allow apps to use HTTP by special permission, and you can be sure that such permission is not easy to get. Not to be left out, in the Android world, use of HTTP has to be specifically enabled in the app manifest and approved by the user. I'm not a great fan of asking the user important security questions like this, but such a practice does discourage the use of HTTP. As a developer of a web application, or an analyst evaluating such an application, you can increase security by disabling HTTP. Most web servers and frameworks make this quite easy. You can also rewrite all HTTP requests to HTTPS, though it's somewhat less secure, as an attacker could still act as a man in the middle on the initial HTTP connection. HTTP Strict Transport Security, Hsts, helps enforce HTTPS by adding the Strict Transport Security header to your web response. This header also has the additional benefit that it prevents the user from overriding an invalid certificate. A nice program initiated by Google is the Hsts Preload list. This list tells your browser to never allow an HTTP connection to the sites in the list. Google maintains the list, and you can apply to have your site added to the list. All the major browsers use this list to enforce HTTPS-only access. You can add to the security of your connection by assuring that cookies will never be sent over an insecure connection. You do this by adding the secure attribute to your request header. In addition, you can prevent cookies from being used in a JavaScript request by adding HTTP only to the header. The second thing we need to do to have a secure web session is to use session IDs correctly. A session ID is a unique string generated by the server to associate the activity of a user, client, with the identity in the server. You should get a new session ID every time that you authenticate yourself to the server. You'll often have a session ID even for anonymous access the first time you make a request to a server. Session IDs are most often stored in cookies, so automatically sent to the server with each web request. Since they are stored in the client, you have to assume that a malicious web client could modify them if they wanted. There are really no restrictions on what you can put into a session ID, but here are some good characteristics and guidelines. Note that if you're using a web framework, it will generate these automatically for you. So these are some good points to check to see if your framework is doing this correctly. First and foremost, a session ID should be hard to guess. That means a persistent attacker can't easily impersonate you. This means simple patterns like small integers or something like session 001 are not effective protection. You can also include a timestamp in the session ID to make it easier to know when to force the user to re-authenticate themselves to the server. Here's XKCD's, one of our favorite cartoonists, take on how to generate a good random session ID. Note that the number 4 was randomly chosen at the time the function was written. We often hear advice that you should encrypt your session IDs, which are typically stored in cookies. While there's no real harm in encrypting them, you really don't get much benefit from doing so. Since you should always be using encrypted HTTPS connections, the cookies won't be visible on the network. And if someone does manage to compromise your browser or server, then they'd be able to get the cookie values anyways. There are some cases, mostly involving very large data centers, where encrypting a cookie can interfere with the front-end processing of a web request. In these cases, part of the cookie value may be used to quickly decide which backend server can best handle the request. One case where encrypted cookies can help involves the cross-site scripting attack that we mentioned in part 2, where we showed how JavaScript code might send your cookies to a third-party server. However, the HTTP-only directive in setCookie can help prevent such attacks. We should be conscious about the scope of a cookie. As we mentioned in part 1, unless you specify differently, a cookie for bank.com will also be sent along with a request for credit.bank.com. You can control and limit such use with the domain directives in the setCookie header. You can also add additional constraints on cookie use with the same site directive. The third and final piece of our session management puzzle is the inclusion of a large random value in each web request. The random values are called nonces by cryptographers and often called tokens by web programmers. The basic idea is that the web application server embeds a random value, a nonce, in each web form that it returns to the browser. The nonce is often included as a hidden field in a web form. As a hidden field, it will be transferred back to the server, but is never displayed to the browser. Since this random value comes from the server with each form, and since it is not a cookie, then the attacker will not know the value, and the value will not automatically be sent to the server, as happens to cookies. In our previous attack scenario, the attacker convinced the browser to execute some injected JavaScript. That JavaScript won't contain the nonce, so would be rejected by the server. In summary, we've seen 3 important issues that you must address to have secure web sessions: secure connections, sensible session IDs, and nonces. The combination of all 3 of these provide a solid foundation for secure web requests.
Okay, here we are back again. So we brought together several pieces. Now, you know, as we said in the video, if you're using a well-designed web framework, it should be giving you, it should be dealing with session IDs for you. It should be putting nonces automatically into your web forms. And of course, unless you've told to do otherwise, it should be requiring you to have encrypted sessions, HTTPS sessions, which, by the way, even though we call it SSL, the protocol has moved on to TLS, now TLS 2.0. But everybody generically calls it SSL, but there's actually a new protocol because those old protocols were found to have weaknesses. Moved on. Okay, so let's see. And where we are right now is, you know, we talked about some basics. We talked about cross-site scripting and how that can manipulate a request. We talked about cross-site request forgery and how an attacker would attempt to make you do operations you couldn't do. And then we said, well, if you do these 3 things, they should help you build a strong session and prevent these kind of attacks. So we're going to look ahead at one more kind of general problem, which is called redirect. But I want to see if we have some questions, time to ask a few questions, or share any thoughts if you. You're all scaring me because you're all too quiet. if I was teaching in front of one of my undergraduates and the room was as quiet, I'd probably do something really outrageous and get everybody, or ask them some really ridiculous question.
There is a question in the chat.
Is there a test in cloud? I missed. I don't have a question. There was one about endpoint vendors, which we answered, and there was a comment
And
about
a nice comment below.
nice comment, but I don't have a. If I missed a question, please ask it again. Here we go.
Sure that for questions we are using Zoom and not who.
Oh, Larry says you have a hand raised. Please. Yeah, if you asked your comment on Whova not in Zoom, we'll miss it because the instructors are dealing with it. So Larry said you had your hand raised. Please go ahead. You'll need to unmute if you want to talk.
Yeah. No, I was just checking on that question in the chat room.
Oh, okay. Okay, great. Great, thank you.
There is a question by Eric on the chat.
Okay. Okay. How do you see any examples? Examples, Eric. Examples of which things are you asking about?
Yeah, sorry, I typed really quick because I thought you were going to move on.
So okay, good. You caught us.
Clear with my question. I guess I was meaning, how often have you found code where you've looked at it and gone, "Ooh, here's an example where someone could take advantage of your web application, and you should make this adjustment on this, server side or however you fix."
Pretty often. It's if you want to read a nice piece, and I'll try to put the link. We'll try to get the link put up or sent out to you. The work we did on cybersecurity for maritime shipping, we actually did in collaboration with a company that runs 40% of the container terminals worldwide. Their software runs those terminals; they don't actually operate it. And we found a bunch of web issues of including lack of encryption and bad session management and too much information and other. There's lots of kinds of things that we're only giving you a taste of in a session like today. And in our most recent assessment that we did for Trusted CI of somebody in the NSF cyber infrastructure community, we found some related topics. That report will be public and we'll be able to share it, but I can't tell you. I can't share it now, but soon it will be public so you can actually see.
Can I ask a
Yes, please.
Could you find those vulnerabilities from an external facing scan, or would you have to be on the inside of the network and see the code?
That is a really good question, because essentially what you're asking is what's the difference between penetration testing and in-depth assessment of the system code. So, and we run up against that all the time. And the answer is some of one and more of the other. So for example, for the company Total SoftBank that we did the maritime assessment for, and I can mention them because they and us were so happy with the process and where it went and the fixes that we actually published together. So we joined public. So there's a company, actually as a side comment was, we did an assessment on them. We found problems, we helped them fix it. And we kept telling people, tell everybody about this. People will get excited that not that you had problems, but that you have a process and you're fixing things. They got a mega contract from Maersk as a result of being able to demonstrate to the world their security process. Way back when, the first team we ever assessed was the Condor Group. Condor is very public about their security processes, and that's only done them good. So, so getting back to the question, so this company wasn't using HTTPS, forcing HTTPS And that's something you could have picked up from a penetration testing scan. There was also places where they're giving out too much information back with returns, or not doing authentication right in their web queries. There's no way a penetration tester could get that, because you'd have to know something about how the information is being used. So penetration testing is a great thing. They can catch a lot of good things. They have a fixed bag of tricks which they look at, which are good bag of tricks to look at. I'm not trying to be disparaging, but it's limited in the kinds of things it can find, and it won't find it won't find new kinds of things, where these in-depth assessments that we do will find it. And so, but the goal as a programmer is for us to teach you on the developer side a lot of these things not to do, and that way, whether it's pen testing or in-depth assessment, you know, you're safe against that. And as we said in the beginning of the presentations, you know, there's no way we can tell you everything about this kind of security or software security in general. We have a whole semester's worth of material that undergraduates sit through like 40 hours of lecture, your typical semester, on this stuff. So what we're trying to do here is get you to think like an analyst, think like a bad guy, as we said in the beginning. So you look at your code differently, and then this is hopefully the start, or maybe an intermediate checkpoint to the next learning activity you have to get further on there. So, okay.
And also related to that question, when we were in our assessment, we find that in general, if a system is vulnerable to, let's say, cross-site scripting or cross-site request forgery, it will have kind of many web-related vulnerabilities, and it's not like they have kind of only one. So it means that if they have issues, it's kind of they're kind of weak security-wise, and we were able to find different web-related issues. Obviously, we're talking about web applications.
Okay, good, thank you. Okay, other questions or comments anybody has on these topics so far? We have one more session on web security, and then we'll have some time for Q&A, and then we'll have a break, and then we will, after the break, take up briefly looking at how a little bit about how software assessment tools work, and then you'll be able to get your hands on and actually do it and find some of these kinds of vulnerabilities that we've talked about in these units. So if there's no further ado, let's go on to redirect.
In this module, I have been talking about threats and attacks that affect web applications. Our objective is to learn about redirect attacks, both basic open redirect and more complex versions. Then understand some of the challenges that arise when trying to deal with such attacks. Open redirection is basically a feature in which the web server takes a request and redirects it to another website. If your website supports unrestricted open redirection, then an attacker could provide you with a link that appears to be for your bank, but on closer inspection will actually send you off to evil.com's website. Inspecting the URL might lead you to see the redirection. However, the attacker can obscure the contents of the URL using percent encoding. Here we see the percent encoded equivalent of the original URL. Let's look at an example of how this might work. We start with a phishing email sent to you ostensibly from your bank, but of course it's really from an attacker. First, let's note that it contains a URL like the one we just saw. Second, if you pause for a second and carefully read the email, you'll see a clue that it's a phishing message and not a legitimate one. Now, if you were unfortunate enough to click on this link, And if your bank supports open redirect, hopefully not, then you'll end up at a website actually on evil.com. And that website will send you back a web page that is frighteningly similar to that of your actual bank. Of course, there are ways to try to be careful here, such as checking URLs before you click on them, and checking the URL in your web browser once you reach the website. But we'll see that even these measures might not be enough. There is some good news though, and that is that your bank probably does not support open redirect. So the number of places to which you might be redirected is small and are all partners of the bank, such as bank.com redirecting you to creditreport.com. Any well-managed website that supports redirect will have such a curated list of permissible sites to which a redirection can go. This kind of list is called a whitelist, where we list the permitted activities, not try to exclude all the non-permitted ones. And a bit of more good news. Many browsers will now ask you first before submitting a redirection. Redirection is not going to go away soon. Search engines like Google or Bing use redirection in the links that they provide to you. When you click on a search item, it first takes you to the search website so they can track your click and generate statistics or billing, and then they redirect you. There have been some proposals to get rid of such behavior by adding a new attribute to web links, the ping attribute. However, these features have created their own controversy. And here's a different and more recent form of redirection attack. And this one is a bit more complex and tricky. The general scenario is that an attacker sends you a link that would appear to generate a legitimate request from Google to access your G Suite resources such as Google Docs or Gmail. It does this by first registering an application that will first attempt to access your Google G Suite resources like Docs or email. The attackers first create a website with a name reminiscent of a legitimate site, here called googledocs.g-docs.win. Then they register this site with Google as one that will operate on G Suite resources. When they register it, they call their app Google Docs. These registrations are handled automatically, and this fake name wasn't caught. Now, if you click on this link, you will invoke a complex and widely used authentication protocol called OAuth 2. As part of this protocol, Google will be careful and ask you if it is okay for this app to access your email, contacts, or whatever. And when it asks you if it's okay, it will ask you if it's okay for Google Docs to have this access. If you say yes, the attackers have just gotten access to a lot of your private content. You can be easily fooled into saying yes, and even an experienced person looking at this long, complex link will have a difficult time detecting the fraud. Let's add to the worry with a more recent kind of attack, called an internationalized domain name homograph attack. Basically, a homograph are two things that look alike, but actually different. For example, the lowercase l and the number 1 can be similar in some fonts. Zeros and O's can also be similar. That's why we often put diagonal lines through our zeros and horizontal lines through our 7s. But it's gotten a lot worse. Let's say you see this URL in a link or redirection. Could you trust it? Now, you're an experienced security practitioner and very suspicious. So you look carefully and decide tentatively that it looks okay. So you click on it and get taken to that website. Once there, you look at the URL and see it looks just the same, so you're more confident. Then you see the lock symbol indicating HTTPS and click on it to see the digital certificate. The certificate appears to be from the same domain name, so you're even happier. So you log in with your apple.com credentials. Unfortunately, you've been owned. What look like the English letters for Apple are actually the Russian Cyrillic letters with the same appearance. However, they're definitely not the same letters and definitely didn't take you to the apple.com website. The attackers registered this look-alike name and even got a digital certificate for that site from a legitimate certificate authority. If you were super paranoid and copied the web address from the link or from the browser and pasted it into your Vim or Emacs text editor, you would have seen that there were not typical English characters. That's a level of carefulness and paranoia that most people don't have. You have to be careful out there. We've now covered several topics in web security, starting with basic web concepts, then cross-site scripting, cross-site request forgery, secure sessions, and now redirection. In this latest part, you've seen that there's some significant challenges out there relating to really assuring yourself you're visiting the site that you intended. Getting the details correct is so crucial here. As we mentioned at the start of this module, this is just an introduction to web security, but now you've got a foundation on which to base your future explorations.
Okay. I personally find those homograph attacks rather terrifying. It requires you to go to a level of scrutiny which is more than most of us do on a daily basis. There is research out there that's trying to deal with this. I heard some work where they're trying to actually take the image of the URL, then running it through image recognition, then processing it in the simplest, the Roman alphabet, and then seeing if they're aliases. There's a lot of work that's being done out there. There are no definitive solutions. Companies like Apple, an example, are busily trying to buy up those domain names. But there's so many high top-level domains now. It's really hard to do. But they're trying to buy them up as they anticipate variations that the attackers haven't gotten to yet. So, and I do want to say one more thing that came up in an earlier video. We record some of these pieces of the videos recorded a while ago, and they're using the terms white and blacklist. We find we as a project and as the security community, we're deprecating these terms and using blocked and permitted lists instead. We should not be using white and black for good and bad, permitted and not permitted. So so that needs to be updated in our material. So if that caused you any stress, we apologize for that. That will be fixed in the next revision. So like to see, so want to take a moment, or as long as you need, to catch up on quizzes on any of the web material. And then what we're going to do, since you have been a little bit quiet, we're a little bit ahead, so we're going to do the tools video, then do our coffee break after the how tools work video. But first, we want to see if there's any of these, if you have any questions related to any of the web materials.
And then the tools video will be our last video, and the rest of the time will be the hands-on session.
That's right. So the hands-on session should be interesting because you'll actually get to do this. I will say, you folks, I'll use the unflattering term of guinea pigs. We have not, this will be the first time we've done the hands-on session in a virtual format. Though we did teach last semester our software security course last spring, and in March, like academia everywhere in the world, we were thrown into a virtual environment rather abruptly, and it ran it all, and we were doing active teaching, so where the lectures were online and the exercises were in the live sessions. So we have done this quite well, but this is the first professional tutorial that we've done since we've been forced online. So hopefully it'll go smoothly. It should. So okay, something chat question mentioned little bit about current research, browser, any cutting edge developments in browsers mitigating some of these attacks. There's been a steadily increasing attention to isolation as programmers find new ways of doing cross-site attacks. They've been ratcheting up that tighter and tighter. I think the area which I've seen the most recent attention, and there's nothing out there yet, but I'm hoping for, is dealing with these homographs. Now people are saying, well, if you've been visiting apple.com and you get something that's, however you say the Cyrillic equivalent of some of those letters, gets that, just some people have talked about, can we just do a diff and saying, can we generate equivalent sets automatically of letters? And then can we map those on and detect when you're using something, a non-standard element out of the equivalent set. Maybe you always use the Cyrillic APPLE. If you use the Roman APPLE, that should be a warning, and vice versa. So there's some stuff going on there, and I said there's people who are experimenting using image processing of the URL field to reduce that down and seeing if, so that's the place where I know is the most new stuff, and that's from Sean 1 and from the other Sean, thank you for the comment. Other questions or comments on here? Okay. You know, we look forward to your feedback, and just a little bit looking ahead, we'll mention it later. There is a survey at the end, and we really do appreciate the comments. Just so you know, there were some comments and questions of a tutorial we taught actually down in Australia last year that inspired a whole reorganization of the web stuff. So your feedback helps us get better, so we do really appreciate it. Okay, let's, I don't see any other questions or comments, so let's, since we have enough time, let's cover the how tools work video, and then at the end of that, we'll do a time mark and of when everybody should come back to start the hands-on.
Welcome back. Now I'll be introducing the important topic of software scanning tools, also known as static analysis tools. Using these tools is a key part of any programmer's workflow. I will give you some background on the code analysis. Later, we'll show you how to use these tools to improve your code. Our objectives are to learn a little about the history of static analysis tools, then learn how they work, their limitations, and how you interact with these tools. The overall goal is to make you more effective when using these critical tools. When you use a static analysis tool, you start with a program in source code, bytecode, or binary code form, and scan the program with the tool to get a report on what problems were found in the program. Note that these tools are static, which means they don't run the program. These tools just look at the code in source or binary code form to understand what the program might do. Now, your first line of defense is the compiler. In the process of analyzing your code, the compiler can detect many potential problems. Compilers use warnings for problems that are not in violation of language standard, but indicate risky behavior. For example, in the GNU and Clang C and C++ compilers, the -w format option causes the compiler to check that the types of the elements in a printf format string match the listed variables. You should turn on as many of these warnings as you can handle. They'll help ensure that your program behaves as you intended. You might think that in GCC or Clang, -w all is really all the warnings. It now includes quite a few, but not all the possible warnings provided by the compiler. Programmers get upset when new options are added to this list. So, GCC and Clang introduced the -w extra option to make the list more complete. Use -w all and -w extra together. And if you want to be careful, you can use the -pedantic option to make sure that you get warnings that strictly adhere to the ISO language standards. The Microsoft Visual Studio compiler makes life a bit simpler here. /wall means all the warnings. At Bell Labs in 1970, Ken Thompson and Dennis Ritchie introduced the Unix operating system, a groundbreaking and important innovation. The original version was written in assembly language. In 1973, after much discussion, Dennis Ritchie introduced the C programming language, and version 4 Unix was then rewritten in C. You have to understand that C was quite an advance from the typical assembly language approach taken by previous operating system teams. The C compiler was pretty primitive in the kinds of things it checked in the code. So, in 1978 at Bell Labs, Stephen Graham introduced lint, a program that did a variety of interesting and innovative checks on the C code. Along with the basic analysis of the program's control and data flow, it could check for things like variables being used before they were initialized and reporting if a calculation might overflow. The invention of lint spurred the compiler writers to improve their code analyses. So as lint got smarter over the years, so did the compilers. All the static analysis tools you find today can be considered descendants of Graham's lint. So these analysis tools are designed to find flaws in the code, or as we define the term in our introduction module, find weaknesses. The weaknesses may have come from simple mistakes, or perhaps were placed in the code intentionally. Ideally, you should run these tools from the very start of your software project. However, even if you have a mature project, you should use these tools. Before any commit to your software repository, these tools should be run and the weaknesses addressed. These tools parse your program and then apply some level of analysis to the code. We'll talk more about the kinds of analyses that they do shortly. It is important to note that the tools don't know what the program is intended to do or how it does it. Instead, they look for specific programming errors in violation of good programming practices. The tools are structured like a compiler, but instead of producing a binary as output, they produce diagnostic messages. Let's talk now about the capabilities of these tools. Ideally, these tools are accurate in that they don't miss important weaknesses, false negatives, and don't report too many non-existent weaknesses, false positives. You also want the tools to be fast. If they are too slow, programmers simply will not use them. You also want them to check lots of different things, from memory to injections to races and many more. The unfortunate reality is that no tool can do all three of these. At most, you get 2 of the 3. Typically, tools sacrifice precision for speed and number of checks. There are a variety of technical decisions that the tool author can make, and these decisions will affect our tool's speed and accuracy. For example, a tool can simply look at the syntax, the pattern of program text, or semantics, the meaning of the program. Syntax-based tools are fast, but they can easily be misled. For example, they may simply look for the pattern of text, like the name of the often dangerous Unix function popen. Semantic-based tools, on the other hand, try to understand what the program is doing. So if they saw a call to popen, they would see if the parameter value could originate from the user. If you're doing semantic analysis, you can evaluate each procedure or function or method, whatever term you like, separately, or you can look at how they interact. If an operation in a function could be safe or not, depending upon an input parameter, then you have to look at how the function is called to really know if there is a problem. This type of analysis is called interprocedural analysis and can get complicated to implement and expensive to run. Another form of interprocedural analysis is called whole program analysis. Many tools will evaluate your program one source file at a time. So if a function is called from a function in another file, then you won't see the interprocedural effect. Few tools do whole program analysis. Many weaknesses are only apparent if you understand how a variable's value is calculated. For example, is a subscript out of range, or will an integer calculation overflow? These can only be determined if you can follow the calculation in the program. This is called data flow analysis. This kind of analysis is complicated to implement and can be difficult, if not impossible, to give accurate results if the calculation is based on user input, or if the program uses pointers or arrays. We'd like our tools to tell us the truth. This means if there's no report for a line of code, then we know that there are no weaknesses of the type reported by this tool present on that line. And if there is a report for that line of code, then we know it is true. Such a tool, in the mathematical terms, would be called sound. Unfortunately, no tool out there is sound. Implementing such a tool is either too slow in the general case or just impossible. Mathematically, we call that undecidable. And the tools, especially the commercial ones, don't like to tell you when they're unsure of what they are doing. The implication of these characteristics is that they affect a tool's speed and ability to accurately report what might be wrong with your code. Now let's look at a simple example and see how some of these issues come into play. Here's a simple line of code in C, though it could be in any of a variety of languages. The call to execl takes the name of an executable file as parameter and causes that program to run. So the question is whether this line of code is safe. If we had a tool based on simple pattern matching, it wouldn't be able to know what program was being executed. So it would have to conservatively tell us that this line of code is dangerous and leave it up to the programmer to verify. Now let's assume that the preceding line of code assigned to the variable cmd the constant string pointing to the ls program. A semantic analysis tool would see that a known safe program is being executed and say definitely no. Well, I write this with a squishy phrase, sometimes definitely, because these tools are unsound. Now let's change the preceding line of code to one that reads the CMD string from user input. Now the user has complete control over what program is executed, so the tool would say definitely yes, it is dangerous. You're not controlling what the user is doing to your system. Let's make this a bit more interesting. Now the value of CMD is a result of calling the makeCMD function. Because we don't know what makeCMD is doing, we can't say whether the execl call will result in something dangerous or not. However, if the tool did a procedural analysis, we might be able to know what's going on inside of makeCMD and get a more precise answer. When a tool analyzes your program, it may create a variety of different representations of the code. Some of these representations include ones that capture the relationship between classes, ones that model the program as a state machine, and from the compiler world, ones that represent the control and data flow in the program. Tools that represent the data flow will try to understand the expressions that capture the value of the variables using a technique called symbolic evaluation. Think of this technique as a kind of simulation of what values the variables might take. These abstract variables are expressions that describe a variable's type and possible values. This kind of analysis is based on an extensive body of work in compiler theory and program analysis, using techniques like abstract interpretation and model checking. One way that tools have to make results more accurate is to be path sensitive. This requires keeping state for each possible alternative for control flow. For example, does the tool separately track the possible states for the then and else branches of an if statement? Or does it simply represent the union of the possible state changes from both branches? Another way that tools can make the results more accurate is to be context sensitive. This means tracking all possible paths in the call graph so you can do interprocedural analysis to see what effect the caller state has on the callee. Both path and context sensitivity make the tool more complicated and slower. So we get a list of weaknesses from the tool, and many tools will try to grade these weaknesses based on the severity, potential for exploit, and how certain the tool is. The goal is to use this information to prioritize your efforts as to which weakness reports you investigate first, or ever. You, as programmer or analyst, have the responsibility to look at these reports and decide if the report is correct, incorrect, or just not relevant. There is the challenge of dealing with potentially long lists of false positives and the unknown unknowns, the lurking false negatives. While these tools are automated, the decision of what to do with the results is controlled by you. As I just mentioned, you have to first decide if the weakness is a true weakness, and then if it leads to a vulnerability. Once you've made that determination, You have to decide if the risk associated with the vulnerability is serious enough that it's worth your time to fix. For weaknesses that you will fix, you then have to identify the strategy for remediating them. Something that experienced software assurance practitioners know is that there's no silver bullet, no single tool for a given programming language that will be best for all your needs. Even though the commercial vendors want to lock you into their tool and tell you that's all you need, our experience has shown that this is not the case. There are a variety of reasons this is true, including variation in computing environments, variation in algorithms or heuristics that are used by the tools, and the fact that new exploits are developed all the time. Now let's look at a simple example of how this is true. If you run this piece of Java code through several tools, you might find that PMD tells you that variable y was never used. Spot bugs tells you that you didn't check this return value. JLint warns you about using equal to compare string objects in Java. Equal tells you if you have the same object for strings, not if they have the same string value. For that, you need to use the equals method. Spotbugs also warns us that we didn't close an IO stream on exception. NESC Java tells us that the array index I is probably too big. Note that the for loop should test less than length, not less than or equal. Also note that we didn't report any results for commercial tools. That's because the tool vendors forbid anyone from publishing any results about how well they work. A terrible situation indeed. Some of the things that analysis tools are good at finding include style problems, pointer errors, buffer overflows, races, resource leaks, and some injections. However, there's some things that might be difficult but not impossible to find, such as the use of weak passwords, incorrect access control list settings, or weak keys for cryptography. We note that there is recent research that is improving the checks for passwords and crypto issues, such as the CryptoGuard project from Virginia Tech. And some things are just not appropriate for tools to check. These include a bad design, code that doesn't implement the design, configuration issues when you install the program, or errors based on the way different programs interact. As we mentioned, basic data structures used by many code analyses are the control flow and data flow graphs. For control flow, we create the CFG, the control flow graph, that captures execution order and branching. For data flow, we annotate the CFG with data flow information to reflect how data flows through the computation. The basic idea of the control flow graph is simple. We divide the program into basic blocks, where each block represents a sequence of statements. Any place in the code that is the target of a jump or call is the start of a basic block. A jump ends the basic block. A basic block also ends at the start of the next basic block. This definition sounds a bit legalistic, but when you look back at the graph I showed, it turns out to be pretty intuitive. As a last issue, I'd like to talk about when you should use static analysis tools. The answer is not that complicated. Always, every project. They're easy to use, and even though they don't solve all your software security problems, they can make a noticeable improvement. On a new project, you just run the tool every time you get ready to make a commit. You knock down the weaknesses a few at a time when they occur. However, on a legacy code base, if you applied an analysis tool, it would be like turning on all the compiler warnings. If you had 100,000 lines of code, you get close to 100,000 reports. But there is an effective approach to this problem, one that we've used successfully in our own software projects. You start with a simple but strict rule. Every time someone commits a file, there must be at least one fewer weakness report from the analysis tool. If you follow this rule, you'll get control of the number of weaknesses in a few months. Of course, this is monotonic, so will steadily decrease. And with a shorter development cycle and the release cycle of today's software, you'll make good progress. But more important is that for programmers, fixing these weaknesses is like eating potato chips. You can't eat just one. They'll fix a weakness, then probably fix another and another until they finally get bored or distracted after 5 or 10. The result is that you'll clean up your code base more quickly than you thought, without making anyone too crazy. You now have a basic idea of what static analysis tools do, how they work, and their limitations. We also talked about your role as programmer or analyst when working with these tools. You're now ready to move on and try them out.
Okay, so that wraps up the video portion. So what we'll do is we'll give you a chance for some questions on this topic or even reflecting back to the previous topics. And after the questions, we'll take a break and then we'll dig into the hands-on for you more venturesome souls. Questions or comments? Or is everybody just desperate for some caffeine?
And during the break, I'll leave an URL on the screen. That's the slides we'll be using during the hands-on session. So if you need to go, back some slides, or you want to go ahead and go kind of move forward, you'll have the slides. So that's the URL I'm going to leave on the screen now.
Okay. Got a question. Thoughts regarding scanners such as Zap, around those that operate at the compiler. Zap is a different kind of tool. It's really it's a proxy tool for intercepting communication. So it's more of a dynamic tool than a static tool. And so what we've talked about in this section is very specifically, we've talked about static tools, tools that that specifically look at your code without executing it. They could look at your source code, they could look at the Java bytecode, they could look at the actual binary, though there are fewer tools that work at the binary level. Now, there are a whole bunch of tools that are dynamic tools. These are also important. We just haven't talked about them here. So these dynamic tools might be something like that. Scan your website and try to throw stuff at your website. There might be things that just get in the middle and just listen to the communication going back and forth. They might be tools that monitor your execution. If you ever used a tool like Valgrind, which runs your program and checks to see if your pointers and buffer allocations are fine. They're really good for C and C++ to see if you've got buffer overrun. So there's a whole other category of tools called static analysis tools, called dynamic analysis tools. And dynamic analysis really falls into several categories. In that category is also fuzz testing tools, which basically are input generators that generate just random input, unstructured or structured, to see if your program is behaving well. It's a way of exploring whether you can own some bits in an unchecked part of the program's state space. Those tools are important. Static analysis tools as a class are easy to run because you really only need the code. It doesn't even have to be run. You'd like the code to be able to be built, compiled, but it doesn't necessarily have to run. And they can still find things. Dynamic analysis tools require you to be able to run the program, which means not only to compile the program, but have an environment that's compatible with all the OS and library versions being compatible, and having data sets. And if it's going to use a server somewhere, you're going to have a version of that server running. It's trickier. It's more complicated to use a dynamic analysis tool. Now, if you're a developer and you're developing some software, obviously you have a test environment. Your test environment becomes the environment you can run your dynamic analysis tool. So, but it's harder for somebody else to run that tool. Static analysis tools are easy to run. Okay, in terms of static analysis, aren't there issues dealing with, say, browser-side JavaScript code? You have to get that's a good question. You have to get a hold of the code. So the people writing the browser are the ones who are going to have to check the browser side JavaScript code. Because remember, that code is delivered to you from the server, from the web app. So that if that code is dynamically generated, then that creates a whole nother problem. And a lot of times the JavaScript code that's generated in the browser in the web world is coming from your web framework. So there's really no, you actually didn't write that code. That's coming from the web folks. Actually, that leads to another point which we haven't talked about today, but it's interesting that your code is probably a small part of all the code that gets executed. Your code probably uses libraries and frameworks or classes or modules or whatever it is. So you write this much code, but then you're using code from all these other people. And that's those tools, that software, the framework, the numerical framework, the web framework, the database framework, the storage framework, whatever, those parts of software are part of your software supply chain. There are things on which you're depending. And there are tools which will actually check the National Vulnerability Database to see if you're using a version of Web Framework Foo version 2.0, it will actually look to see, are there known vulnerabilities that are worrisome? Are there known issues that are worrisome for Web Foo Framework 2.0? So
yeah, actually, we'll do that later today.
Right, and so yeah, so there's the tool is called the Owasp Dependency Checker that doesn't actually scan the code. It looks at the versions of the things you're using and checks to see if there are known vulnerabilities in your supply chain. So you want to make sure your code is not creating brand new big holes to drive the attacker's attack truck through. But if you're using all this framework, you'd like to make sure that the components you're using don't have any serious vulnerabilities. In the last web assessment, in the last software assessment we did, we found the project that we assessed, we're using 3 frameworks that had worrisome, 2 had very worrisome issues, and 1 had a should really fix it kind of issue. So that's kind of related to this question. Okay, other questions or thoughts or comments? Absolutely, you may share these slides with your colleagues, absolutely. And as a side note, we do presentations at different organizations, at government labs and universities and places like that. We even do companies, but that's it. And we can customize the topics and the languages and things like that. So if you're looking for, if you're dealing with injections of various kinds or numeric errors or buffer and overflow errors or exception handle errors, there's a bunch of topics we're not going to get around to today because this is a big topic. We can talk about, and we'll also share a link to our online resources, which you're welcome, which are open and public. Okay, so it is coming up on the top of the hour, plus or minus 5. Let's assume at 1/2 I won't say which time that is because we're all in different, many of us are in different time zone, but it's coming up at the top of the hour. At 1/2 the hour, we will start with the hands-on exercises. And we'll basically go through, walk through the exercise, and Alyssa really does a great job walking you through so you can be the analyst hands-on there. See you all in 34 minutes-ish.
Welcome back. Let's start working on the hands-on part of the tutorial. So here. So I hope kind of everybody has the handout. So, you know, now I can not kind of be walking around and see everybody's screen. So if you fall behind, you can follow through throughout the handout. If it's too slow, you can look forward. And if somehow I'm going kind of too fast or too slow, just let me know. Okay, this is the first time doing a hands-on exercises remotely. I mean, 100% remotely. So I will need your feedback at real time. Okay, so we'll be working with an application we developed that it's called WizClick, and it's just a simple game. But the point here is that this application represents has features that happened in kind of applications we use continuously in our regular life. For example, here users can transfer points from one user to another, and that's what, for example, we do with our banking application, right? Transfer some money from one account to another. Or you can see someone else's profiles, and that happens all the time in social networks. Or when you read a review, you are reading you're reading what someone else has posted. So the features of the application represent what happened in real world applications. And we'll exploit the vulnerabilities in this application. And then we will use automated assessment tools to see what the tools report on the vulnerable application. WizClick is a web server, it's a web application. We have a web server, which is a Jetty. A client connects throughout a browser. And for database, we use MongoDB. And with any web application, the client sends requests and gets responses. And for authentication, there will be a cookie containing the session ID. And we also will exploit that file. The first thing we're gonna do is to spend some minutes getting familiar with WizClick. There are two accounts you will be using. One for the attacker, username is attacker, password the attacker, and a different account will be for the victim and password the victim. Keep that slide kind of handy in case you forget the password. And if you kind of break anything and you want to reset everything to the initial state, the state things are right now, you run those commands. Okay, so anytime you're going to do something and you're unhappy with the result, you want to have start from kind of from scratch, you reset the database. First thing, we'll run WizClick, and if you have any questions, feel free to interrupt me kind of through the chat or raise your hand at any time. To run the web server, please do that now. Open a console and run these commands. Change the web attack and the run command. I'll give you just some moments to do that. And after you do that, open the, I left the web browser open for you, and actually you should have that on one of the tabs, but just go to the welcome page on the local host.
We should try to get some confirmation that when people get to this stage. So it'd be really helpful after you start this, if presumably you have your, well, first of all, I'd like to get confirmation everybody's got their virtual machine running.
So I will need help with that because when I'm running the presentation, I cannot see the chat window. So,
okay, I got one yes from Wade. Any, if you don't have the virtual, got another one. So if anybody's having any difficulties, thank you all. Oh, lots of yeses coming back in. That's great. If anybody's having any difficulties, this is a good time. If you don't get the VM running, the rest of the exercise, of course, won't happen. Thank you all for the acknowledgements. Great. Okay, appreciate the feedback.
okay,
I'll keep watching it.
Keep me posted with the chat.
I will keep you posted, and you run on ahead, please.
Okay, so when you go to the welcome page, this URL, you get a a window like this, and here is when you authenticate with username attacker, password the attacker, and then go for it. And here we have the application. Our main menu is on the top right, and we can do a few things here. Let's start with ranking. I will then I'll show you a few things, and I leave you a few minutes to play with the application because I need you to be familiar with it. With ranking, you get the rank of 5 users with have the most points in the game, 5, and you can click on the username, and then you get to see the profile of that user. And you may also want to have those names handy because you will want to use them when we will be doing transfer credits. When the way to play this game to earn credits is to click this button in following the earn credits option.
So Alyssa, a couple of things coming up on the chat.
Yeah.
One person saying, I'm getting no such file directory after typing /run/sh command. So it sounds like they may not be in the right directory.
Okay, how do you do this? Let me go back. So you need to go to CD web attack from the main directory.
It said already changed directory.
Do something. I'll show a few slides, and then you share your screen with me, and I'll be able to, hopefully I'll be able to help you.
Yeah, and the person asked about a terminal. There's
okay, what I'm gonna do is I'm gonna share my my virtual machine image and show how to open a terminal and do those commands. So I'll stop sharing the presentation right now for a minute, and I'll share my, okay, I need to, will take me a bit to switch to open my VirtualBox, just so I'll do that in a minute. In the meantime, I want everybody to play a bit with the application, do the earn credit thing, and also the transfer credit. And we'll meet here in 1:11 in a few minutes. Okay, I'm sharing my screen here, and so but who was the person?
Posey.
Okay, Posey. Are you in this directory? And
Yep, I'm in that directory. I followed all the instructions on the screen, but I just get that error. So I double check my syntax is correct.
Do a PWD, please.
All right, just a sec.
yes, I have too many.
I'm in the build classes. I'm in the classes.
And then did you do, in and here, did you do that run sh?
Yes, that's where I got the error.
And you just do ./run sh, try that again. Are you doing the dot? Like it's
the correct syntax. I've got it perfectly, but it's just giving me the error. I'm in the right directory.
Okay, and did you type it exactly how I'm showing you in my screen?
Exactly.
Type ls and see what's in the directory.
I can see run.sh in the directory, but I don't know why it's not.
But okay, probably you are not typing that dot. You know, it's dot.
I am typing the dot. Yes, I am.
We're going to have to see your screen.
I'm sorry, I can't share from this one. I've got two different systems up, but I appreciate you guys. Please, you guys just move forward with the rest of the class and I'll watch.
Okay.
I'm okay. I'll get back to you in a bit. Okay, let's go back to. So you have please answer in the chat if you had a bit enough time to play a bit with the application and get a feeling of what it does. But you're getting any answers? Did you get any answers as for people have had time to?
I got back one response positive. And so does anybody have any issues? And we're a small enough group that you don't have to chat. You feel free to unmute and just speak up.
That will be very helpful to me because I cannot see the chat window. So, and that will be fantastic. So please do so.
But does anybody need any more time or should we move forward? Okay. No comments. So why don't you keep it moving?
So the vulnerabilities we will be exploiting now will be the ones we have on the screen now. First, we'll start with cross-site scripting because that's our way of kind of probing the system as an attacker. And then building the real exploit will be cross-site request forgery. And also, you know, it's super kind of, with cross-site scripting, it's very easy to get and anybody's cookies, kind of cookie, including, for example, the session ID cookie. And then we want to learn how an attacker could use that cookie to impersonate the user and do something that will benefit the attacker. Our first thing will be to investigate if WithClick is vulnerable to a cross-site scripting. And we'll do that in the easiest way, which is kind of make a pop-up alert window to up on the victim side. The first thing we have to do, that will happen kind of with any attack, is to find the attack surface for our attack. So in our case, we'll go to in WithClick, we'll go to the My Account page and use the profile field. And so the attacker will be changing her profile in such a way that when the victim goes and sees the attacker profile, it will get the pop-up window. So we are here in the attacker's page, we click on My Profile, and we type some JavaScript code, in this case, to show an alert window with this content. So please do that. And please say vocally when you are done with that.
Got it.
Great, thank you. And then
Got it.
open.
All good.
Fantastic. Then let's do two things. First,
well, if anybody's falling behind, please give a shout so we can try to keep everybody moving together. Don't worry about it. Just let us know.
So we are going to do kind of two things now. First, in that same window where you were, reload the page. And now you should see the alert window popping up. And then go and open on your browser a private window. So we need it to be private so it doesn't have access to the same cookies as the in the other like the cookies kind of the attacker is using now. So you can really log in as a different user, and you can have two users at the same time. So open that window and log in as a victim. The username was victim and the password was the victim. And then the victim goes to see the attacker's page, and then we'll get that pop-up window. So now I'm the victim, and I go in ranking, and I click on the attacker's name, and I get to see the attacker's profile. And instead of saying, oh, the attacker, it's an expert, whatever, we see the pop-up window. Please do that.
And Alyssa, the person who was having problems with the directory rebooted and is now operational.
Oh, great, Posy. Good to hear that. And then we'll try to do something a little bit more interesting at this point. And we want to get the victim's session ID cookies. To do that, we'll do exactly the same. So, I mean, nothing challenging here. We'll go to the attacker's profile, and instead of having the alert window with some random string, we'll have the document that will do alert document.cookie, basically to see the cookies for that user. And then here we see things a bit differently, because when the user runs, when we refresh that screen, the user will see the user session ID cookie. And when the victim clicks to see the user's profile, the victim will be seeing its own cookie, which will be different than the attacker's cookie. So here we got the victim's cookie, but still not very interesting because it's the victim seeing its own cookie. So we'll have, after, I'll give you some a few minutes now. After the attacker changes its profile to display the cookie, and the victim checks on the attacker's profile, we have again the victim seeing its own session ID cookie. So please do that, and we'll continue to do kind of some damage in a couple of minutes. And let me know if you have any questions.
Yeah, Lisa, for some reason, I'm not seeing on the attacker's profile, I'm not seeing the edit option under my profile anymore.
Oh, yeah, I know what you did. That's probably because when you did the previous attack, you probably forgot the script tag, the greater than or something like that.
Well, I put the terminal script tags in. I entered a regular script with a terminal script tag. But yeah.
Don't believe you. So
I just reset the
reset the database and okay. Just go directly to that and make sure. Yeah, I mean, yeah, because that happens when there is no end of the script tag, and the system doesn't have any way to know that when the end of the script happens. So yeah, just reset that, and then you'll have the edit button and be able to do that. And then if you have time, try to do a kind of a fake or a wrong closing script tag, and you will see that the edit button disappears. I feel like kind of flying blind here because usually I will be walking behind and seeing your screens. That's kind of
All good.
different. Great, thank you.
I'm all good here.
Me too.
Okay, so I'll go forward a bit more and then let me know if I need to kind of slow down, okay? Now we are moving to cross-site script, to cross-site request forgery. Now, because we can do cross-site request forgery because we know that the application is vulnerable to cross-site script. And our goal here is basically that the attacker will make the victim execute a request to transfer some of the victim's credit to the attacker themselves. So first, so basically the attacker wants to steal some of the victim's credit. And to do that, we need to learn how the transfer request works to kind of mimic that request. To understand how the transfer request works, we go to, in the web browser, we go to the developer mode, and we are still we are the attacker, right? This is the attacker screen, and the attacker needs to learn how the transfer works. So to do that, first the attacker will do a real transfer in the transfer window. But for example, it will say, I will transfer to the victim 0 point, right? I don't want to lose any point, right? So here you can type to the victim point like 0, for example. And we open the developer mode to see what happens when we do this transfer. And when we do submit, we'll have a post method for this transfer. I mean, we'll get a post method, and the file that's executed is transfer. And well, we see here the URL. And then I'll want you to click on the parameters to see. I'm going to answer that. We don't pay attention to that right now. The parameters to the transfer are victim. Well, the name of the parameter is 2, the value is victim, and the same 4 points to transfer, value 0. And with that information, the attacker will be able to recreate, to mimic that transfer. Now I'll show you how the attacker will do that. But what I was mentioning right now is the process to understand how to learn about what the attacker needs to do to do something wrong. Now we will be using the same profile field for the attacker. And now I'm going to explain this code line by line, but that's basically the code to create a request. And then when the victim sees the attacker profile, then this request will get executed. And this request is saying transfer to the attacker some points. So how does this work? First, we need, this is possible because the application is vulnerable to cross-site scripting. It's executed JavaScript, and we create a new request. To do that, okay, this says new XML HTTP request, but this means create a new HTTP request. I mean, the XML thing, I don't know really why it's there, but okay, fine. It's just forget about the XML, it's about creating a request. And then request, rec.open, this is not opening anything. This is specifying what time of the request are we creating. We're saying we are creating a post request, and we learn from the web inspector that that we want to execute, but it's on the transfer file. So that's why we have transfer here. And the third parameter is to mean, refers if the request goes in an synchronous or an asynchronous way. In this case, it's asynchronous. And then we need to specify the parameters, right? Because we want to say, oh, transfer to me 10 credits. So we use this method, set request header, and saying, and here we are saying, we are adding an HTTP header to the request, and here is the name of the header name, and here's the header value. The name refers as how are we going to pass the parameters to this request. And here we are saying, oh, the parameters will go kind of encoded in the URL, and that's what we are going to do next. When we send the request, we will say that we will be sending the post request to execute what's in transfer, and the parameters will be the parameter 2, and the value is to the attacker. Like if it was a GET request, but it's not a GET request, it's a POST request. And the points to transfer, okay, we are transferring only one, but you could use any number you want. And you save that as the attacker's profile, and make sure if you are doing copy paste from the PDF file, do it. I will suggest do it cut and paste to a text window first, right? Like the notepad or something like that, and fix the quotes. Because if you do cut and paste from the PDF, the quotes are likely to be funny, and then it's not gonna work. So make sure you have it just on an ASCII text editor like Notepad or something like that. And check that the quotes are exactly as I have them. And then you save that on the attacker's profile, and then as a victim, go to the attacker's profile, and we'll see that some points will be gone just by the attacker seeing by the victim just seeing the attacker's profile, they will lose points. Are you with me at this point, or are there any questions? Okay, I'll ask differently. Are you following me?
It didn't work. I'm just double checking. I typed everything in correctly.
Yeah, probably it's a quote. Make sure.
Yeah, I made a mistake with a quote, and it
Yeah,
showed
that's super common. So different question. Is there anybody who needs help at this point? I'll give you a few minutes to work on this. But no matter what system you are trying to attack or defend, the way of doing this is the same, kind of learning how their request you want to mimic works, and then replicating it.
Yep, got mine working.
It's working, cool. Then I'll wait a bit here. If you wish, you can go ahead with the next slides.
Yeah, I got it. I had ww4 URL encoded, not form.
Oh, okay. Where?
That's what my problem was. I got it working. left off the
so you're
N
saying I
on
have a
form.
typo here.
No, I had the typo.
Okay, so yeah, that's super common, right? And if you're doing cut and paste from the PDF to avoid the typing, the problem is the quotes get funny. And of course, to test this, again, you need to go to the victims. You need to be the victims and try to load the attacker's profile. And note that, for example, that attack could also succeed if you are logged to your bank and get distracted. And while you are logged to your bank, you go and check a review for a restaurant. And in that review, there is the request to do a transfer from your bank. And in that case, the attack will be successful and will happen exactly what we are showing here. Okay, I could use a little feedback from the rest of you. You need more time, or where are you at this point? Tell me something. Anybody needs help?
It's looking okay for me.
Thank you.
One person said an additional person in chat said they're ready to go on. Anybody have any issues they'd like help with to help them keep moving?
Okay, I'll go ahead a bit more. Now, we are still doing cross-site request forgery. And what we want to do now is that the attacker has such a profile that when the victim sees the attacker's profile, the victim gets infected. And when someone else goes to the victim profile this time, that person will also be infected. And so we'll have kind of a chain of infections. And in addition to that infection, we will include the code we had before. Tim, I'll suggest, please, the code that you have right now in the attacker's profile, cut it and paste it on a text window, because you may need that code again. So you don't want to type it again or clear all the quotes again. So save that code in just in an ASCII window. And now, to do that, first, we need to learn how to change the profile. So to do that, we do exactly what we did before. So that's not new. It's just that the only difference is the name of the method, right? When the attacker changes their profile, we with the web inspector, you see the post method, and you see that the file that is involved this time is account. And also when we go and see the, okay, and then you click in, you will also click on parameters and see the exact value of the parameters. The result is exactly basically what we did the same, what we did before, but we are calling this time account, and the name of the parameter is value, and the value of the parameter in this case is okay, hacked. So please, and we will use that because this will get a bit more interesting in a minute. So check this, try this code as the attacker's profile, and the interesting part here is seeing that while doing this, we are changing the victim's profile. So you will need, again, the attacker, that's the attacker's profile. The victim sees the attacker's profile, and by doing that, their own profile gets changed. So please check that. Probably the easiest way to get this working is cut and pasting your previous request and changing, instead of having transfer, having account, and changing the values here. That will be my suggestion at this point. Let me know when you find it, when you see it working, please. Or also if you have problems, also let me know. I'll choose someone at random, or maybe not at random. Kay, how are you doing there?
I ran into like a little weirdness. I put the script in, and then it didn't look like it did anything. And I went back and looked at from the attacker's profile. I looked at my own profile, and then it changed my profile to hacked. So it cut out all the scripting, but it just says, just submitted the value hacked. So make sure you refresh the page as the victim. Is it that it seemed to be caching it or something?
Yeah, I was going to say that. I mean, you need to refresh. Yes. Actually, when you type that the value for the attacker, and then you refresh it on the attacker side, and then you you need to either go from the victim side, either go to the attacker's profile, or if you are there, you need to refresh it.
And Alyssa, we got a chat from Kay saying she is all good.
Oh, okay, thank you. Was totally random. Now what we are going to do, and then after I'll give you a few minutes.
So we got one more chat in there, Alyssa. Dannon says, I'm good to go. I spaced out and closed the terminal tab when poking around. Took a second to figure out that I killed the web server. So Dannon, you back up and in business?
Yeah, I'm good now. I just, it took me a second to realize what I'd done.
Oh, I know. There's a lot of tabs, a lot of windows, and in different contexts, so it's easy to do.
And probably a small screen, so if you combine all those, yeah.
Yep.
So, now, now we learn how to change someone else's profile, right? So now we change the attacker, change the victim's profile. But now what we want to do right now is kind of implement this chain of, let's say, attack. Now that if someone goes to the victim's profile, that that third person will get also infected. So to do that, the first thing we need to replicate itself. So I'm going to explain you this code. Our goal is having a script that replicates itself. So basically, we want to show that we are able to do that. So our goal is to show an alert window, just like a printf, right? But just to see our result, and our goal is to have the script we see on the screen and have an alert window that shows exactly the same script that we have on the screen, meaning that that's the replicated code. But basically, we have this script on the screen, and we want to have that in a variable to have that exactly same code. So to do that, we need 3 parts, and I'll start actually from the bottom. We need the JavaScript code that we will want to execute, or the same JavaScript code we have here on the screen. And we need a header tag, basically saying this is the script, and a tail tag saying, /script, we are closing the script tag. So let's start with the tail tag. The tail tag is just /script saying, okay, end of the script. The header tag, it's, okay, beginning of the script, saying, okay, script, and saying the name of the content of this script will be replica, which is exactly what we have here. Basically, we are putting in this variable header tag what we have here. Okay, we could do with or without this type element, but basically we want to have script ID equals replica. And the core of the script is, we have it in JS code. JS code is basically saying everything that is in the element replica goes to that variable. And we see the element replica is actually this script, right? Because we have here the name, the ID of this replica, of this script is replica. So what we are getting here is everything that goes between the script tags, which is kind of from var to the alert that goes in JS code. And before that, we have the opening script tag, and after that, we have the closing script tag. Again, the opening script tag, we say it's script ID equals replica, which is what we have here, and the closing tag is /script, which is exactly what we have at the end. So use that as the attacker's profile, like we were doing before. Please do that. And when you reload the profile, the only thing you'll see and what is expected is an alert window whose content is exactly the same code that created that, that window. So when I'll go back to this screen again. But basically when the attacker reloads its profile, you basically see the same code that it's on the profile. And then we will use that for, that's a replicated code. And we will use that for this change of infection. So please do that.
Can you back up a slide for a minute?
Sure.
Thank you.
Again, I would recommend probably to do cut and paste from the handout and triple checking the quote.
Can someone drop the link to the handout in the chat? I've been keeping up, just manually typing, but
Oh, no.
that's getting a little.
Okay, I'll do that. I'll do that right now. Okay, we are in 131, so I'll do that for you right now. Okay, right now that I'm not projecting, I can see the chat window. Oh, no, I'm still sharing my screen.
It's in the chat window now.
Oh, okay, thank you.
Thank you, Scott, for doing that.
Just when projecting, I cannot see the screen when the chat window. But again, be warned about the quotes, they will be all messed up. And if you have any questions about any of the methods or instructions or anything on the slides, also let me know. So let me know when you have it working.
I've got it working now. Thank you for the link again.
How are the rest of you all doing?
Doing well.
No problems.
Okay, then let's put the different elements we have been seeing together. So we want to change the profile as you did before. And also we want to use this self-replicating script we just used. So yeah, and in addition to that, given that the attacker is taking all the trouble, at the same time, she wants to steal some credits for all the victims along the way. So what we are going to do is combine all the steps we have seen before. So I'll show them to you here. First, this is the code that we had before that it replicates itself, right? Exactly as we did before. And after that, we'll have the code for transferring credits, right? We did that before. That's the post request that transfer credit from whoever runs this to the attacker. And in addition to that, we want this to be the new profile for the victim. So it's a third person. This is the victim profile. The attacker will get some credits. So to do that, we are doing exactly the same as we did before. We are changing whoever watches this profile, right, by doing what we did before. What's here? Having the account and creating the request for the account, and having, instead of having the value hacked, having the value the replica code variable. And the replica code variable is the one that contains exactly what it's this whole script. So by doing this, we are basically, the victim will lose some credit because they are transferring them from the victims to the attacker. And then the victim's profile will get changed to this. So when then a different user goes to see the victim's profile, also the attacker will get some credits, and the victim and the second victim will get infected. So now you can just do kind of cut and paste of the different parts we have been seeing before, and you may want to check on this. But given that we understand the 3 different elements, I leave that kind of a homework, so we have time to do some other different things. Okay, are you with me at this point?
Got it.
Cool. So to do this, we are not going to do that now, but to test this kind of later, there is a third user Bucky and password Badger. And if that third user goes to the victim's profile, you will see that the attacker's credit increases. Now, remember that, I don't know, half an hour ago, we were talking about getting the victim's cookie. And now, but we had only the victims seeing their own cookie. So now let's have do something so that cookie travels all the way to the attacker, and the attacker can use the session ID cookie from the victim to impersonate the victim and steal their credit. So to do that, we need to do basically 2 things. First, we need a different terminal window. Make sure you use a different one so you don't kill the server. Type, let's create a server that will be listening to port 8000. So just run this on a new terminal window and leave it run. And as for the attacker's profile, this time the attacker's profile will be this script here, which is basically creating an image, and as a source of the image, just saying, go to port 8000. I mean, you could use any URL we want. We are using this localhost. And as a parameter, send the cookies. So the cookies will show up in this guy who was listening to port 8000. So please try that real quick. That shouldn't be difficult.
Got it.
So with the attacker, thank you. The attacker views the victim views the attacker profile, and then it's not any longer the victim seeing their own cookies. It's now their own cookies traveling to a place owned by the attacker, because that usually won't be localhost, obviously, but an URL that belongs to the attacker. And now we know that the attacker can get that session ID cookie. Well, can get all the cookies. We only have the session ID cookie. So now, how do the attacker can use that cookie to steal from the victim? That's what we are going to do right now. And okay, that's what we were doing a moment ago. And here is how the attacker gets the victim's session ID cookie, like what's a parameter that went to an URL to a specific port. Okay, now we want the attacker to use that stolen session ID. And to do that, yeah, for the sake of time, I'll tell you just how to do that. We'll use a REST client. We'll use Postman for that. So please go cd to the Postman directory and launch the Postman application. We need to do that because we use Postman. We could use any REST client, but Postman is very convenient for this. So, and it's a kind of more practical than using the web browser. But any REST client will do. That allows you to modify the cookies. I'll show you how to do that. So please launch Postman. And basically, we'll create the post request. We'll create the post request to transfer the cookies, but we need to impersonate the victim. So to do that, we as an attacker, we will authenticate to the server, but right after we do that, we'll switch the value of the session ID cookies from the attacker's value to the victim's value. We know the victim's value because we were listening to it and it came as to our port 8080, so don't close that window because we will need that value. And in Postman, okay, you close whatever window you get and you click on the plus sign you have, and that allows you, brings you to a screen.
So let's say we have a comment saying, will the VM and the server access remain available after the session is over? I'm woefully behind, still trying to catch up. Actually, you have the VM. Everything you have, all the exercises contain what you have on your desktop. So as long as you keep that VM, you can go through and reproduce this. And you're not using anything external. Everything you're using is internal to your VM.
Because you have the OBA file, which is the virtual machine image, and you have the PDF file with the slides. And in any case, our OBA file here will be available for a week.
And you're welcome to send us email with questions after the session.
Absolutely. Feel free to send us email, and we'll be glad to help out. So as for Postman, can you please confirm that you are in a screen that looks like this?
Yep.
Thank you. So the first thing we need to do is, as an attacker, okay, to go to the same URL we were using from the browser, right? And click the send button. And then we get here, basically, instead of seeing the page, the content of the HTML code, we are seeing the HTML code, right? But that's the welcome page. And we know that after seeing the welcome page, we need to authenticate. The thing we do that now is we need a post, authentication is a post request, and it's also in this URL. And we click on body, because we need to provide the values for authentication, and the values are username and password. And we provide those values here, username and password. Username attacker, password the attacker. And click send. Basically, we're saying the welcome request, which is a post request with parameters username and password. And when we click on send, we'll get the HTML code we get here is the one we have after we authenticate, which is kind of the menu to do the options of the game. And we care right now, we care about the cookies value. So please click here on cookies. And when you click on cookies, you see the attacker's cookie with the session ID and the value of the cookie for the attacker. But then that's where we want to change the value, and instead of using the session ID for the attacker, to use the session ID from the victim, which we already have in our terminal window. So we click here on cookies, and we get a window like this. And here we just copy paste the value. Make sure you don't replace everything. Just replace the things that are between the equal sign and the semicolon. And instead of having the user's ID, the attacker's session ID value, we have the victim session ID value. Okay, and then you click on save. And the session ID value you will have is the one that you got on your terminal window, which is this one. Okay, I took this screenshot after I replaced the value.
So we have a comment from Wade saying, so I'm going back a little bit, I'm getting an error that Python can't open file -m.
Let me check. Okay, I'll check on that one sec. 150. Did you try typing it like I have it here?
At the start of the exercise 3, page 136.
138. So who's having that problem, Bart?
Wade, Wade, you want to unmute and join the conversation so we can help? Oh, you got it. Okay. What was the issue? Copy paste. Okay.
Mm-hmm.
Okay.
Yeah.
Good.
Okay.
Well, there's a lot of details here, so not surprised we get a few of those.
Okay, where was I here? Okay, well, can someone confirm that you were able to change the cookie value?
Yep.
Okay, and then we do what we did before with the welcome. When we were calling the welcome request, now we are doing the transfer request again. And we learned before that the parameters were true and points to transfer. So transfer to the attacker, 1 point or as many points as you want, and make sure that the request is a post, because by default you have get here, so make sure you change it to post and do send. And then do the same thing again, go to the web browser and log in as the victim and see that every time you click send here, the victim loses credits. And this is the attacker, right? Here things started authenticated as, the attacker authenticated themselves and then changed the value of the cookie from the attacker's cookie to the victim's cookie. And now everything the attacker is doing is happening, is basically impersonating the victim. I think this is super cool and frightening. Please try that. Okay, and in the next, well, to check that this works, as I was saying before, in the browser, you can log in as the attacker and see how your credit goes up, and you can log in as a victim and see how your credits go down. And now I want to use the remaining time we have left today to play a bit with tools. We'll use Spotbox, which Spotbox is kind of the best available tool out there for Java. And it's, and actually you could use a commercial tool for Java, but most of the commercial tools have at its core actually Spotbox. So it will be kind of like kosher versions of Spotbox. And some information that you need handy just because Spotbox will ask for it, which is the directories where the source, well, containing our WizClick application. So the Java classes are in this directory. The jar files that the application relies on are in this directory, and the source code is in the directory shown here. So to run Spotbox, you can either type the command that it's in here, because I mean that virtual machine has already Spotbox installed, and the Find Security box plugin also installed, so it's kind of ready for you to use. And if you don't feel like typing all that, I created a script for you in this for Spotbox directory. This is kind of not standard, it's just me creating a few scripts for you if you want to run Spotbox at the GUI or the text interface. And for you to kind of learn about everything that you can do with Spotbox, this is the documentation, the URL. So make sure you execute Spotbox, right? Following either option 1 or 2, please execute it. And then you'll have the interface is a bit, I mean, not great, but, and we go and create a new project. And after we creating a new project, we get a window like this. The project name, you can do anything you want, but there is less flexibility here. Class path for analysis, we use the directories I was showing you in the previous slide where the code is. Then you can spend some time playing and seeing what's on each directory. And now you can quickly check, or believe me that the stuff is what I'm telling you it is. The classes for the classes are here. And oh, for the jar files, it's a bit annoying because I told you the directory where the jar files are, and now you have to click kind of 13 times because there are kind of 13 of those. And you cannot specify just one directory. You need to specify the specific .jar files. So you need to do kind of add kind of 13 times one per file. And yeah, you have to do that. And also, if we wanted to see where in the code the problems that Spotbox report are, which obviously we want, so we need to provide Spotbox with the path to our source code, and we do that here. And then when you click, okay, this is some explanation here. Okay, again, the classes, the jar files, and the source code. And then we click OK, and when you say OK, it will start doing the analysis process. It will take, I don't know, 15 seconds or so. So please do that. And after you do that, you will get your results in a screen like this. But I'll wait a few minutes here, a couple of minutes here. Could you please confirm that you are able to run a Spotbox, please?
Yep, it's running for me.
Okay, thank you.
Yep.
Great. Okay, and after doing that, you will get the results, and the results, for the results, you have the screen divided well, in 4 parts, like we see it here. Spotbox gives you kind of a lot of problems happening with the code. In this case, in this app is not very big, but we get, okay, 66 issues, but we care about the security related issues. There are a lot of issues with coding practices, right, that we are not addressing them today. Today we focus about the security issues, and C25, that's kind of, for such a small application like this, it's like there are issues with the application, which we knew because we already exploited them. And then we click, if we click here on this, on the security folder, we get subfolders for the different issues. And we see, okay, cross-site scripting, only one, okay. But we see that there are kind of more potential cross-site scripting here, which are not really potential. Most of them are true issues. And that we have kind of different problems here. Then that's how we can double click of any of those items and see what's the problem about. So I'm clicking to show you how this works. I'm clicking just on the first one here in cross-site scripting vulnerability. And I get, okay, I'll explain you what I'm getting. Here, and I'm click on this one, in this case there's only one. Here, they explain what's the weakness about. And here I get the code where the weakness happens. that's super. I mean, that's the really the useful part, right? Well, the super useful part, because say, oh, there's a problem with this variable, and if I scroll up, I see where that variable is used, and that will help me determine if the tool is reporting something, a real problem, or if it's a false positive. And here I get an explanation about the problem and suggestions to how to mitigate that. You know, this is kind of for every kind of problem of the same kind, I'll get the same prose. But what's always different is in what line it happens, and how in the code, where in the code it is, and what are the instructions that use the variables that end up in this problematic code. So, and this part of the tutorial, the idea is for you to go through the different list of vulnerabilities weaknesses that the tool is reporting, and trying to see if those are real issues or false positive, or what are the problems about. And here now I'm clicking on where it was saying potential cross-site scripting, and also kind of the coloring refers to the severity of the vulnerability. But let's say that at regards, Spotbox still has some ways to improve. And okay, so I click in that one. I mean, you should go through all of them. And here is the one related to the profile. I'm clicking on this one because that's the one we have been exploiting all the time. So at this point, you should kind of spend some time basically understanding the result of the tool, right? And yeah, you will want to save, just one sec. You want to save this exercise basically, because otherwise you will have to type kind of 13 times again for the .jar files. So you do save as, and you, and then you, if you do this the Spotbox project file, then next time you do just open a project, and then you don't have to, you have the project there and the results there. And I know that I'm going a bit quick here, but I mean, here you need to spend some time and understand the results of the tool. And in general, the way of working is the following. We go through the list of weaknesses reported by the tool, and then here we determine if those are they real problems or false positive. If it's a true positive, then you go and fix the problem. And if it's a false positive, Spotbox allows you to create a filter so that the issue won't be raised next time you run the tool, because usually you fix the problem and you run the tool again to make sure that that you address the problem hopefully in the right way. But if there is a false positive, you don't want it to be told about a false positive 100 times if you run the tool 100 times. So, and the way of creating filters for Spotbox, it's not that great because, I mean, it's not very friendly, let's say, because you have to write an XML file, and that's, I mean, it's not very friendly. It's not rocket science either, but it's an XML file with basically saying don't report again on this problem. And I'm not explaining that today. And then after we fix the problem, we run the assessment again. And for you to be able to have access to the code, I'll show you how to do it. You go to the source directory, you edit the file you want to edit. In this case, for the vulnerability I was showing you, that's the file related to the account. And you will need to fix the cross-site request forgery there. Actually, You need to fix the cross-site scripting that will prevent the attack to happen. And then you need to compile the code to do that. You do what we did before. You compile the code and then you run the server again. And then you test. You need obviously to test that the vulnerability is not there. Okay, that was, I mean, I wasn't expecting you to be doing all the things at the same time I was talking, right? I mean, that's, that would have been, let's say, challenging. But I just want to make sure that you follow the process to do, so you can do that at your own pace. Any questions here, or you know exactly what the way to do to see what's, to understand what Spotbox is doing to this with Click application?
Yeah, I was following along. I got it.
Yeah, I'm good too.
Okay, thank you. And also, before, actually what I will suggest, before running the tool, it will be also good to understand a bit the structure of the application. I mean, where the code for the different requests is. And I'm just going to briefly mention the Owasp dependency checker. And here, the idea is to understand, oh, obviously I'm not building everything from scratch, right? I'm using a web framework. In this case, it was Jetty. I was using a database. In this case, it was MongoDB. And I'm using tons of dependencies, right? I mean, I was just basically doing the code for some specific requests. So are my dependencies, all this software I'm relying on, it's safe, it's problematic? So to answer that question, we use Owasp dependency check. And here, the way to run it is very simple. It's the way I'm showing in this line here. Owasp dependency check is installed in the virtual machine for you. And basically, we are here saying, okay, where is the source code? And the tool generates a file with that name that you and then you look at it with the web browser. To get documentation about the tool, I left here a couple of links for you. So when I open this file with this local file now with my browser, I get something like this. And it's basically telling me about the vulnerable dependencies. And here I'm getting a summary of the assessment. I know that there are 3 vulnerable dependencies. And I get an entry, a row for each of the dependencies that are problematic. And then down below, I get details on each of those 3 vulnerable dependencies. And the tool basically is telling you about the software that is problematic, and they tell you about how severe the issue is according to the Owasp tool, and also how confident the tool is about the result it's reporting, and okay, some additional information. I mean, in that documentation links I show you, there is, they're explaining exactly how to read the report. But basically here, we know that we have 3 vulnerable dependencies. That among those 3, they have 21 vulnerabilities. And those are the components. And to learn about all those 21 vulnerability in those components, we scroll down in the report. So that will be interesting for you to check. Okay, I think I've been talking for a while. It's been kind of a bit quick, so I invite you to do the exercises at your own pace and contact us if you have questions or in case of any feedback. Okay.
Great. Oh, it's been it's a lot of hours to be sitting in front of a screen and concentrating and listening. Really appreciate your attention for sticking through this. You know, we're listen, doesn't rolls her eyes when I say this, but you know, if one of my favorite movies is The Blues Brothers, and we're on a mission from God. We're trying to help all of you try to make software more secure in the environments you're building, environments you're using. And so we're hoping this can make some difference for you all. Any closing comments, questions on this? Anything we can follow up on? And I will just say again, you've got our contact information right there in front of you on the screen. We really do. We really are happy to follow up with you and listen to and try to help out and answer. And if you have things that are going on in your research and your projects, please feel free to contact us and see if there's some way we can help out. So if there's no questions, I'll just thank you all for being so attentive.
Yeah, thank you for your patience and being here with for hours.
Thank you both.
Thank you.
Yeah, thank you.
And look forward to meeting you all in person where we can share coffee, maybe lift a beer later on together. So wrap up and we'll say bye all.
Bye.
Bye.